Hi there, today on the bench, two devices from TIS, standing for Test Instrument Solutions, a UK maker of test equipment mainly for installers and electricians. One is obviously a multimeter, the TIS-258 to be exact. Quite small, but kind of chunky. The other item is in the black pouch. It's some kind of probe, a TIS-1040. I bought both of these as used items some time ago with my own money. Actually, mostly for the probe, the 1040, because I found it intriguing. But I'm also curious how well the multimeter is made, given that the company targets mainly professionals. Let's start with the multimeter. On first glance, it looks like a conventional job with discrete manual ranges, but then not quite. On the right, the current ranges are only split into big handfuls, and it's actually auto-ranging within these. Moreover, for currents, AC and DC are separate, while on the volts, AC and DC are on the same switch, and you have to use cell to switch between them. Finally, we have discrete ohms ranges and temperature and a combined diode and continuity setting. This meter uses the COM and rightmost socket for everything, including microamps and milliamps. Only amps has its own socket. So on the whole, a whole bunch of conventions are a bit mixed up, but I'm sure you could get used to it. Let's quickly go over the specs. Voltage first. On the bottom you see the specs from the manual, and above the results of my tests. On the left is DC volts. Above 2 millivolts, DC voltage accuracy is actually quite good and generally better than its specs. On the right is AC volts. This is not a true RMS meter, by the way. It just about meets its AC specs if you include the ±3 digits on the calculation. Much more noticeable than on DC volts are the spikes, where the error shoots up. This is a 2000 count meter, so at 200 millivolts, 2 volts, 20 volts and 200 volts you have to select the next higher range, and these instances match the spikes here. Let me demonstrate. Measuring 1 volts AC in the 2 volt range and a TIS-258 is very accurate. If I increase the voltage to 2 volts, I get an overflow, so I have no choice but to select the 20 volt range. In that range it reads 1.96, which is a 2% error, way more than the ±0.8%, but if I add the allowed 3 digits, it would be 1.99, and hence it's still in spec. DC volts has of course a similar problem, but since it's overall more accurate, the difference is not quite as jarring. But the meter insists on using AC volts as a default, which is very annoying since that happens after every range change. I'm in the 2 volts DC range. Now the voltage increases to 3 volts and I need to move to the 20 volt range. But when I do, the TIS-258 switches to the 20 volts AC range, so I have to press cell again, which is really annoying if you work predominantly with DC. The TIS-258 has problems if both AC and DC are present at the same time. Here's an example. The meter on the right shows AC on top and DC below. As I increase the DC offset, the AC readings on the TIS reduces to the point of close to 0. There's no warning or any other indication. You need to be careful with this meter and mixed AC and DC, and that applies to both voltage and current measurements. Always use the highest range first to check if such a condition is present. Moving on to current. DC again on the left and AC on the right. In both cases the horizontal axis is milliamp, not amps. It is a very similar picture. DC current is quite accurate once you go above 10 microamps, much better than the specs. For AC current, we have again the prominent error spikes caused by switching ranges and low accuracy at the beginning of a range. As with AC volts, you need to consider the ± digit part, and then everything is still in spec. Once you are above the beginning of a range, AC currents, similar to AC volts, are actually quite accurate. As I said earlier, current measurements on the TIS-258 works in a mix of manual and auto ranging. Right now I'm in the microamp range, and if you look closely on the display, it actually shows auto. When I increase the current to almost 2 milliamps, everything still works as you expect, but at 3 milliamps the TRS would like to uprange, but it can't. Instead, it now beeps and flashes a red light asking you to do it manually. But moving the range switch is not enough to go from milliamps to amps or the reverse. You need to move the probe from the rightmost socket to the leftmost too. If you don't remember to do both actions, you are just seeing nonsense values on the display. Lastly, a quick look at the AC bandwidth and resistance. The bandwidth is specified as 40 to 400 Hz, but it's actually quite a bit better. In practice you can go as low as 10 Hz and as high as 1 kHz without losing too much accuracy, and the 3 dB point is actually about 7 kHz. On the resistance side, the TRS-258 has no rel function, which affects the accuracy of the low ohms measurements, but above 10 ohms everything is fine and the accuracy is actually better than specified. Strangely, the combined diode continuity mode defaults to diode. In my experience, continuity is used much more often than diode. Anyway, let's test it. Okay, a single diode works of course. 2 diodes in series does not work. I think this is the first multimeter I've ever tested that can't measure the forward voltage of 2 normal silicon diodes in series. Of course, that means forward voltage of none of the other diodes work either, and they don't light up. That is really pretty poor. The compliance voltage is only 1.49 volts, but I would have thought 2 silicon diodes should have measured. That's a pretty common case, for example between the minus and plus points of a full bridge rectifier. Can continuity make up for it? Not really, but maybe it's those safety shrouds on the probes, so let's do it without them. No, makes no difference. As usual in temperature mode, shorting the input will show the current temperature of the cold junction inside the meter. 23 degrees Celsius apparently, or 73 degrees Fahrenheit. For a quick test I connected a calibrator. It is set to 0 degrees Celsius and the meter shows 2 degrees. I could get more accurate results by entering the meter's cold junction temperature into the calibrator, but all I want to do is a quick functional test, entering a few simulated temperatures and seeing the meter shows about the right values. And it does. The backlight is quite bright, but short. It times out after about 15 seconds, and speaking of timeouts, while I did not find it in the manual, the meter has automatic power off or APO after about 15 minutes. It is possible that holding one of the keys at power up disables it, but I did not try it. The input resistance in AC volts is at least 10 megohms and pretty much the same going over all ranges from low to high. It's the same for DC, volts going back from high to low, but having to press cell each time to switch to DC. The 200 millivolt range is interesting. In DC mode, its input resistance is beyond what the Bryman BM869S can measure, even in conductance mode, so it must be in large gigohm territory. A high Z mode is a good thing to have, and a bit unexpected in a rather basic multimeter. I'm surprised that it has not been mentioned in the manual. The burden resistances in current mode are as you would expect, and the same for AC and DC. About 0.2 ohms for amps. I need to change the lead for milliamps and microamps. About 1.8 ohms for milliamps, which is not bad, and the usual 100 ohms for the microamp range. All these values include of course the resistances of the respective fuses. And to have a look at these fuses I have to open it up. Let's look at the battery compartment under the tilting bale first. The screw goes into a metal threaded insert, which is nice, but the screw is not held captive and can get lost. It uses a 9V battery, quite amazing, giving the miserable performance in diode mode. And the 9V battery is so tight in that compartment that you need a screwdriver to lever it out. And speaking of tight, the same is true for the red protective sleeve. It is quite a struggle to get the meter out of it. Next, there are 4 self-tappers, one in each corner, that need to be undone. After these steps, the 2 halves come apart very easy. There's a large overlap where the 2 halves slot into each other. This is a good protection method in case a fuse blows while holding the meter in the hand. The display is hidden under a plastic cover, and there's certainly a lot of empty space in the top part of the meter. At least the fuses are large ceramic, high rupture types, not on the level of Breimann and Fluke, but better than many budget meters. Just above the middle socket, the PCB has some markings, HK36T, obviously the OEM. And indeed, the TheHWcave is really the TheHWcave HK36T. I tried to find a manual to compare it, especially about diode mode and APO, but no luck. The fuse for the 10 amp range is shown as 10 amps 250 volts on the PCB, but the one in my meter is actually a 10 amps 500 volt type. 2 wires go off to the backlight. The main chip is a blob and can't be identified. On the right of the blob we have 2 springs that connect to the battery compartment. Right in the middle is a trim pot marked temp. This will be for calibrating the cold junction temperature. Further below, right at the corner, we have a buzzer and then 3 more calibration trim pots. These are actually labeled DC volts, a T with an arrow, and AC volts. The TheHWcave, or rather the TheHWcave, certainly deserves praise for that, because that makes recalibration much easier. Then we get to the 200 milliamp fuse. Interestingly, the PCB offers 2 ratings, either 0.2 amps or 0.5 amps 250 volts. The one in my meter was a 0.2 amp 500 volt type. Finally, there's a single PTC. So protection is kind of a mixed bag. Fuses are better than expected, but the rest could certainly be improved. To finish the review of the TheHWcave off, the battery draw is quite low. Just 1.5 milliamps for all modes except resistance, needing only 0.9 milliamps. Comparatively, at over 17 milliamps, the backlight draws a lot, and the continuity beeper also uses 15 milliamps. Beeping while backlight is on draws more than 31 milliamps, so best avoided. I try to find out when the low battery symbol comes on and if the meter reads correctly until then. In my first attempt, I lowered the voltage to 2.2 volts and below when the meter started to become inaccurate, because I did not see the low battery symbol. I tried again, focusing on the display, and there it is, so high up that it's easily hidden by the bezel when looking from above. The voltage was 2.3 volts, and until then the meter had no accuracy issue. My missing the low bat indicator prompted me to check the viewing angles, and it's very narrow, especially when on the tilting bail and looking from slightly above. But enough of the multimeter and getting to the TIS-1040. On the top we have the pointy end, of course, and on the right, behind a transparent window, is an LED functioning as a torchlight. 2 red LEDs, the left is used to indicate continuity or voltage, the right one is for testing lamps. Below is a round metallic disc, it's just a contact surface. And finally 2 red push buttons, one is labeled test and the other torch. The torch function is self-explanatory. As long as you press the torch button, the yellow LED on the top comes on. That light's not especially bright, but it can still be useful. First, using it as a continuity tester, for example to check if a fuse is still good. There is no on-off switch on this probe. What you do is touch the round metal disc with a finger and then hold the fuse with the other hand and touch the probe tip. So your body forms part of the circuit, and the volume and sound of the beep gives an indication about the resistance. This use of your hand as one part of a continuity probe is very fast and ideal when working away from a bench, like standing on a ladder. Using again a touch of the round metal disc, you can check for the presence of a voltage between 60 and 250 volts. The tester buzzes if there is. This is the high-tech equivalent of those voltage tester screwdrivers with a neon bulb in the handle. I would not recommend using either as a reliable way of detecting voltage. The tester is specifically designed to quickly verify if neon tubes are good. These are still used a lot in industrial settings. In my house, the only one I could find is this energy-saving one. For a lamp test, there's a special test button. Pressing it and just touching one of the neon light ends will light it up. In fact, all you have to do is touch the glass with a tip and you get the same effect. It also works with some LED lights, like this one, but not on all, as this example shows. How does this work? Look closely when the tip touches the light. You can see sparks, a little arc forms. This means quite high voltage is involved here. There is a label on the tester stating that the test voltage is approximately 3 kilovolts at 280 kilohertz. That sounds dangerous, but the current is less than 7 microamps. I can tell from experience that if you touch the tip while the test button is pressed, you can certainly feel it as an unpleasant, stinging, slightly burning sensation, but not as strong that you would jump or drop anything. I was wondering how to measure the voltage because the high frequency rules out a multimeter. 280 kilohertz is in the long wave radio band. I don't have a receiver that can go that low, but here's a radio that can do AM, and the low end of AM is about double of 280 kilohertz. Maybe there's a second harmonic. When the tester is running, the noise disappears because the receiver is swamped with HF energy, and when I release the test button, there's a brief squeak. Then I hit on the idea of using a scope, but a direct connection would certainly fry it. But I have my DIY 1000-to-1 scope probe. I leave the link if you don't have seen the video. I designed it to handle 10 kilovolts and it can do 1 megahertz, so it should be good for this test. I also need to set a scope to expect a 1000-to-1 probe. The test setup feels a bit weird because there's just a probe tip. The return circuit, if you want to call it that way, is over the earth, and the probe is connected to earth via the BNC cable to the BNC socket of the scope. So all I have to do is touch the red high voltage input of my probe with the red tip of the tester and press the button. A nice sine wave with a peak voltage of 1.11 kilovolts and a frequency of 275 kilohertz. The voltage is a bit lower than expected, but the TRS manual states that the 3 kilovolts are only with a fresh battery, and this battery came with a tester when I bought it, and it's certainly not fresh. And speaking of battery, this compartment is the only thing that's accessible in this tester. The battery sits in this little bottom piece and is inserted into the tester and locked in place. Okay, that concludes my review of these two TRS instruments, the TRS-258 multimeter and the TRS-1040 tester. While I can see the usefulness of the TRS-1040 even in this day and age, I must admit I'm a bit underwhelmed by the TRS-258 multimeter, also known as the Honeytech HK36T. I mean, safety-wise it's okay and better than a lot of cheap meters, but there are a lot of annoyances from having to select DC all the time, getting confused by AC plus DC combinations, to not being able to even test two diodes in series or any LEDs. Frankly, I expected better from TRS. If you like my videos, don't forget to like and subscribe and help growing this channel, and consider becoming a Patreon. The link's in the description. Thanks for watching.